to Thursday's edition of Cracking the Cryptic, where today, well, you may be wondering why this puzzle on the screen is yesterday's puzzle. This is, of course, Pythagoras' Nightmare by Matthias J. Raves, a wonderful, wonderful Sudoku, but it's not what I'm going to be doing today because I've already done it. If you haven't tried it, it's in yesterday's video. It is magnificent. But no, the reason this is on the screen is that Mark has sent me a link to today's puzzle, which he wants me to open live on the webcam, and I'm happy to do that. It means that this puzzle is going to have something visually arresting about it, I've no doubt. Something that probably makes it look impossible. But why don't we find out what that is? I will paste this into my browser and click the button, and right, we've got a massive line in the grid. Jörmungandr. What on earth is this word? I can't even say the word. This might be what Mark thought would be funny. Jörmungandr by Jay Dyer. Oh, Jay Dyer. I like Jay's puzzles very much. He is a brilliant constructor. Jörmungandr. I'm probably meant to know what that is. I'm going to guess it's a Swedish volcano. Well, hang on a minute. Let me just look at the rules of this. In fact, why don't we read the rules together? We can understand what's going on. It is a bit weird, though. There are no digits and just what looks like a very long line. Contained within the grid are 9 non-overlapping 3x3 square regions, which must be located. Oh, right, yes, okay, this is big, isn't it? Okay, well, why is it doing that? Okay, hang on, I don't want that on, I want that, that's better. Let's put numbers on. 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is an 11 by 11 grid into which we've got to locate 9 non-overlapping 3x3 square regions. Okay. Each region contains the digits 1 to 9 once each, such that no digit repeats in any row or column. Cells outside regions do not contain digits. Along the line, each time the line passes through a region, the sum of the digits on that pass sum to the same value. If the line passes through a region multiple times, each pass is summed separately. This is an equal sum line. What the blazes? Okay, that is probably the most daunting thing I've ever seen in a Sudoku. You are kidding. So this is... I'm tempted to pause the video while I go off and cry. This is it's ludicrous. So let's just... If you've never seen equal sum lines before, what this is saying is, let me just draw in a 3x3 region into this grid. That's saying that in this puzzle, every time this line enters this 3x3 box, it picks up some number of cells. Let's say it picks up, I don't know, 8's worth of cells. So that would mean these 3 cells sum to 8, and then the line dips out of this box again. So the next time the line jumps in the box again, this point, those 3 digits would sum to 8. And then these 2 digits would sum to 8 when it enters in for a third pass. So it actually, well, if this was a 3x3 region in this puzzle, I would be able to tell you now that this wasn't, that the number was not 8. But the reason I'm saying is I've got no clue how we can possibly solve this. That is absurd. So literally, it's a Sudoku made up of a line. That's mental. That is absolutely mental. I'm going to read the birthdays. Emily Williams, it's your birthday today. Emily is one of our most cherished commentators, Emily's comments, if you read under almost every video we do, Emily will write something erudite and kind and interesting. So Emily, we are very grateful that you exist and you follow the channel. And your husband Byron let us know that it's your birthday today. So I hope you have a brilliant birthday. I hope you get to see me solve this, because I rather fear that this is going to be impossible. Yeah, and obviously I hope you have a great deal of birthday cake. Other than that, I've got to say very well done to those of you who've managed to solve more of you have solved the doctoral pack over on Patreon at the moment. This is this incredible reward we've got for June. From Panthera, the Asylum and Grockles, and the following have managed to solve it correctly in the last 24 hours. So Sarah Turvia, Jules Chang, Leon Viegels, I think, Kyle Manning, Steve Harding, Michael Stranieri, Osher Lerner, and Gregory Sivakov. All of you successfully solved it. You sent the correct entries in, so very well done. Those of you who are still working on it, you've still got till the 20th to be in with a chance in the competitions. So do try and get your entries in the next 4 or 5 days. Now, I've got nothing else to tell you. I am feeling utterly daunted by this. This is, well, let me say for the record, before I even attempt this, that this exists. This is one of the greatest Sudoku creations in the history of Sudoku. It's a Sudoku made up of a line. It's so stupid. It's so stupid. And now I've got to solve it. Oh, by the way, as well, and now I should say this, I have got the alarm man coming in about an hour or so's time. So if the alarm man turns up, I will have to pause the video. I'm guessing that if I'm still going in an hour's time, I won't have finished the puzzle. So it may be that may be necessary. Right. Now, I've read the rules. I sort of understand them. I do not know how we're meant to use them to solve the puzzle. Do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. What? I've got a massive line. I've got a massive line. I've got to draw 9 3x3 boxes into the grid, and it is square boxes. So this is a so-called deconstruction puzzle, which we have done but on the channel before. I know one thing about a deconstruction puzzle, and that is that it's always true in a deconstruction puzzle that row 3, column 3, let's find that, that's there. Let's just make that purple. This has to be in a region in this puzzle. And the reason for that is not the region for that is, but the reason for that is, let's imagine this wasn't in a region in the puzzle. Well then, because we're constructing 3x3 boxes, you couldn't put any of these top cells in a region in the puzzle. So this entire region would be sort of unavailable. And now if you're faced with the task of putting 9 non-overlapping regions in the remainder of the puzzle, you can't do it, because you can only put 2 now in the top in this section, because if you put 1 there, you can't fit. You can only fit 1 more in. There's not enough space to fit in 3 along the top, and that means that you need to put 7 regions into this section of the grid. And because you can put no more than 2 in this column, again, now you're faced with the task, and hopefully you're seeing where this is going, of putting 5 non-overlapping 3x3 boxes into that section of the grid. And again, the reason you run into trouble here is you can put in 2 in any sort of street like that, and you could put in another, let's put those in, and then you could put in another 2 like this. But you can see there's never any space for the 5th region. And that logic, which, hang on, let me down now, get rid of all the colours. That logic applies. It's sort of a, a jigsaw type logic, I suppose. That logic extends. I think this cell is the same, this cell is the same, this cell is the same. Basically, you get this sort of weird pattern in the grid. It looks something like this, and then I run out of colours at the bottom, so I'll start repeating colours. So each of these coloured dots is in a different region of this puzzle. And hopefully, certainly that should be very clear for these four, because you can just do that by rotation of the logic I just showed you. But similarly, if this wasn't in a region, let's imagine we drew in a black line here. To the left of this black line, you can fit one 3x3 region, not two. To the right of it, you can fit one, not two. And then the logic from there flows in exactly the same way. You're tasked with putting 7 regions into the bottom of the grid, and you can't. And then obviously a rotation of that logic to this, and this will prove those things. And hopefully you can see it's the same logic for the middle. If this isn't in a region, you can only put one region to the side and one region to this side. So you can only put 2 in this row effectively then, and you'll run out of space above and below to put in the necessary 9 regions we have to put in. So I'm not sure whether this helps, but I'm going to avail myself of my knowledge of that in the hope that it is useful. But what we don't know, of course, is we don't know, for example, let's look at this. We don't know whether it's going to be right up there, or it could be right down there, or it could be there. We just know this cell is in what is in effect region 3 of the puzzle. So let me just draw in a region anywhere. Let's just have a look at this region and see if we can understand how it might work if this was a region. So then we'd be saying that these 4 cells here are the same sum as those 2 cells and the same sum as those 2 cells. And this cell, which is not on the line, well, that's just not on the line, isn't it? That's just yeah, that's a fly in the ointment as well, isn't it? Because yeah, that's it. I had an interesting thought then, but I think that thought is, I was wondering whether they're all, given what I've just drawn in here with these colours, is it necessarily the case that there must be a 3x3 region in this puzzle that is entirely line? Because if that was the case, that would be interesting in terms of working out how the value that the line must take. I'm not being very articulate here, but imagine there was a 3x3 region in this puzzle. I'm trying to spot the problem is I keep seeing cells that are not on the line. In fact, maybe that's what I've got to do. Let me just highlight all the cells that are not on this line. So those 2 are not on the line. That one, I think. That one. Gosh, this is like scanning Sudoku digits. It's very difficult to be sure you're actually seeing them all, because this line it sort of just plays with your head. That one maybe. Hang on, let's highlight those and see if we can spot any more. That one, there's another one there. Now, have I missed any? I don't think I might have missed one. It actually would be quite important if I have missed one, because what I was thinking was, given I know that each of these coloured digits is definitely in a region and in a different region, is it necessarily the case that there's a 3x3 region in this puzzle that is entirely got line in it. Because if that was true, then we would know that as the line dipped in and out of that region, it must pick up all the digits in that region. And we know from the secret that the digits in any complete Sudoku region will add up to 45, because that's what the numbers 1 to 9 add up to. So if that's true, then however many times that boundary is cut by the line must divide exactly into 45. In other words, the region sum line number would be a factor of 45, which would be at least new knowledge. Now, the problem I'm seeing here is that all of these coloured circles can hit these. No, right, okay, this is good. Right, so I now am going to say for certain that there is a 3x3 box in this puzzle that is entirely line. And the reason for that is that there are only eight black dots, I think. So it's incredibly important. It's incredibly important I haven't missed one, because if I have missed one, that logic doesn't work, because I think each of these coloured circles can absolutely overlap with each of these. Yeah, so if I've missed a blank cell, this logic is invalid. So we've got to be incredibly careful about this, because it would be a 9th dot, and therefore we could allocate the dots, 1 to each coloured region. I'm not seeing another black dot. So I'm going to allege now that there is a 3x3. I don't know where it is, but let's say it's here. Let's just draw one in. Oh, Sven's adapted the software so we can draw diagonal lines now. Right, so let's imagine this is a 3x3 box, a real 3x3, because a 3 box in this puzzle. So what I'm saying is that because this box is entirely got line in it, then you can see that this line comes in here, it picks up 3 cells and then exits, and then it loops around here, then it comes in again, it picks up 5 cells and then exits, and then it looks like it just shaves a cell off there as well. So that would mean, so this, right, well I think this is not a line then, because unless I'm misunderstanding my own thought processes, the problem with this would be because the line enters this box exactly 3 times, that would suggest that 45 divided by 3, which is 15, is the correct sort of total that's being picked up by the line every time it enters the box. And that's impossible because I can't write 15 in that cell. So this is a sensible thought, but I think what we're proving is this is not a 3x3 box in this puzzle. So what now do we have to do? Well, we have to work out what possible factors of 45 work for the value, if you like, for each pass, how much the line is picking up on each pass into a box. So I can immediately rule out any number that is less than 9, and that's because, again, let's draw in the 3x3 box. Let's draw in that 3x3 box, although that's probably wrong as well, but I'll just draw it in. But obviously one of the numbers in this box is a 9. So it's not possible that the sum of the digits on each pass is less than 9, because even if that's the 9 there, that would be suggesting that the equal sum total for every time the line enters the box is 9. and it can't be less than that because it must pick up a 9 in this box somewhere. So actually, this is really interesting because the factors that we're left with of 45 are 9, 15, and 45 itself, which might be what the trick is here. Although that, I'm now going to say that cannot be true. If it was 45, if the number was 45, so that's saying that every time the line enters a 3x3 region, it does a wiggle and it picks up all the digits in the 3x3 box, and then it exits the box, and then it never goes back in that box because it's the number is 45, and then it goes in another box and it does a wiggle, and then each time it enters a 3x3 box, it's got to stay in the box before it leaves. And that would imply that I could divide this grid, and more importantly this line, into 3x3 wiggle sections. And that looks absolutely ludicrous. That looks completely impossible. I can't actually see one place where I can draw a 3x3 where this line would stay in a 3x3 before exiting it. I mean, that one's about as close as you can get. No, and that's nowhere near. Hang on, let me just try and find. There must be somewhere where we can do it. Nah, I can't find it. I can't find an example of where I can do this. I mean, that. No, there's nowhere. There's just no. I don't even think there's one place I can do it. So what I'm trying to do is to draw a 3x3 around this line so that the line stays in that 3x3. So the line enters the 3x3 once and exits the 3x3 once, having visited every cell in the 3x3. That's what I'm trying to see. Well, I can say for certain there aren't 9 of those. I can't even find one of those. So 45 is not the number. So now we're looking at either 9 or 15. Have I missed a factor? I haven't, have I? Prime factors of 45 are 3 and 5. So no, I haven't. So it's right. Okay, so it's either 15 or 9. Now, I reckon it's more likely. What do I think it's more likely to be? I reckon it's more likely to be probably 15. Because if it's 9, that's not very much, is it? Yeah, I mean, if it was 9, it would be very constraining, for example, because you could immediately rule out things like that as a potential box if 9 was the total, because this line would have to pick up 5 cells before it exited, and the minimum 5 cells would add up to is 15, which is quite suspicious. And you can make 15 in a domino. So I reckon it's going to be 15, actually. That feels more likely. How do we prove that? So, So if it was 9, well, the thing I'm wondering about 9 is where the box in this puzzle is that has all its digits on the line, because that line must enter that box 5 times, because it must enter it, pick up the 9, leave it again. Then it must enter it again at some stage, pick up a 1 and an 8 and leave it again. Then it must enter it, pick up a 2 and a 7, leave it again. Enter it, pick up a 3 and a 6, leave it again. Enter it, pick up a 4 and a 5, leave it again. So there must be a point, for that to be possible, there must be a point in this grid where I can draw a 3x3, which is almost going to have a star, maybe here. It's going to have to sort of wiggle in and out of the box lots of times and only pick up 2 cells each time. I'm not very good at visualizing this. No, that's not it. That one. No, that's not it. This. Oh, that. No, that's not it. I don't know where we're going. I don't know where this is, but I'm not certain. I'm not certain. I can be sure that it doesn't exist. So. Okay. Here is an interesting question. So let's imagine that 9 is the number, and we're hunting for this 3x3 box in the puzzle that is completely covered in line. Then how do you ever get to the middle digit of that box? Because what I'm thinking is, given I can only take 2 cell sequences, because I've got to only reach the total of 9 each time, and I've got to cover the whole box, so I have to do this thing where I go 1 8 out, 2 7 out, etc. How do I get out when I touch the middle digit? Now, the only way I can get out when I touch the middle digit, I can't go in and out, because that's going to mean I've taken 3 cells in a sequence, and that's not going to work. So the only way this works is if the end or the beginning of the line is that middle cell. But that doesn't work here, does it? Because, oh, whoa, I'm drawing pretty patterns. So this can't be the middle of a 3x3 box. This absolutely can be, but only in a way that's not helpful, because although I could absolutely make this work with something like that, and then we exit, and then we could come back in and we could grab 2 7, that's all working beautifully. But look, this does not work, because the sum of those 5 digits is going to be a great deal. It's not. I haven't entered and exited this box nearly enough times to make it possible for 9 to work. So this is good. This is good, because now I don't think 9 works either, because you can't deal with the middle digit. Therefore, I'm going to allege. I think I've proved that 15 is the number that we're looking for here. But how does that help us to pinpoint the positions of the regions? So what we cannot have is a situation where the line takes six continuous cells in a 3x3, and that might allow us to limit where the boxes can go. Like, yeah, okay, could that be a box? And I want to say now no, because a box of this nature, 1, 2, 3, 4, 5, 6, and we know that 6 cells, 6 different digits in a Sudoku would add up to at least 21, the triangular number for 6, 1 plus 2 plus 3 plus 4 plus 5 plus 6. So this couldn't be a 3x3 box in this puzzle. But I don't even really know how to pencil that. What would be incredibly useful is if you can't put a black cell. Why would that be? If you put... Of course. No, you can't. I've got it. You can't put a black cell in a 3x3 box now because it's 15. But then the reason for that, obviously, is that Actually, let me try and pick a slightly more sensible one than that one. Let me go for this one. I don't really like that one, actually. Let me go for this one. I don't like that one either. I'm trying to find something where it looks reasonable with the... I'm failing miserably. It's actually quite difficult to put this in. Let me just go. I'm just going to go for this one. This might be a silly one as well. I think this was a silly one as well. But let's try and think about how this might work. We know that as the line enters this box, it picks up 15's worth of digits and then it leaves again. And as it enters down here, it picks up 15's worth of digits and then it leaves again. Let's imagine it never came in here, just for the sake of argument. But the point is that this cell would have to equal a 15 in order for the box mathematics to work. Because we know that the box overall adds up to 45. And we know every time the line enters it, it picks up 15's worth of digits and then leaves again. So whether the line cuts into the box, if it cuts into it only 2 times, it's going to pick up 30's worth of digits, and then this is going to have to be a 15, which it obviously cannot be. But if the line enters it 3 times, then this has to be a 0, and it can't be that either. So that this has to be... now, what would work, actually, but it's impossible here, is if you could put 2 black digits in the same 3x3 region, because then you can make 2 digits in a Sudoku add up to 15 with 7, 8 or 6, 9, and the world would work. But here, because of the way that Jay has positioned the blank cells, or the cells that are non-line cells, you can't put 2 of them in a 3x3. So none of them go in a 3x3, and that is going to be massive, because now we can actually start to... Well, I can make more black cells immediately. That cell's got to be black. If this can't be in a 3x3, that most certainly cannot be, because it would include this one. Now these 2 cells can't. None of this can be in a 3x3. Now these 2 can't be. Oh, this is so clever. This is so unbelievably clever. These 2 can't be. So this... No, not. I was going to say that one, but these 2 certainly can't be now. It makes it look like these want to be, doesn't it? Let me just see. That one can't be. Ooh, okay, let's look at this green region here. Because this green region, now because it can't take these cells, and it's in a 3x3, it must take these cells. That pushes the yellow over, which pushes the purple over. And now how does the purple become a 3x3? There's only one way. Given it's entered column 1, we can purplify all these digits. And that is our first region identified. And now we can blacken those. They can't be part of a 3x3. Now the other thought I'm having now is I've got to be careful here. Because when I was trying to draw my 3x3s around the black cells there, because I know the number we're heading towards is 15, I can never draw that, for example, as a region. And the reason for that is that this cell, and in fact this cell, are now impossible. Because as the line enters and exits, it only picks up 1 cell on its route. So this would have to be a 15, which it cannot be. So in drawing any of these regions now, we have to be careful to make sure that we're always including at least 2 cell strings. So, yes. So here's a point. How could this yellow region here, come down to this row? Well, it can't, because this is going to have to be a 15 if we do that. That pushes the yellow upwards. Alright, here's another little trick. If the yellow took this stretch, now look at its nature from a line perspective. The line enters here and picks up 5 cells, exits, and then it comes back in here and picks up 4 cells and exits. So all 9 digits in this are picked up by the line here, but it's only entered and exited twice. So these digits should therefore add up to 30, but we know they would add up to 45 because they'd be all the numbers from 1 to 9. That won't work either. So that's not right. So that means this is not in, which means this is in. Holy moly, I actually think we might be able to solve this. And that is a very exciting thought. Right, this can't be green. Because if that's green, this cell has become a single cell again. So that's green, and that's another 3 by 3 identified. So now I've got the whole top of the grid done, and I can get some more black digits here. Now, what next? Oh, well, given that this is a black digit, this orange must take those, which means the orange must take those because it's a 3 by 3. And yes, okay, so if it took these 3, what's happening here? It goes in and out, so this would have to be a 15. In and out here as well, 15 again, that won't work. So it must be those 3. These have to therefore turn black. This is now ringed by the magic ring of green. This cell here is now not capable of being in a 3 by 3. This is not capable of being in a 3 by 3. This yellow must therefore take those 2, which means that we can extend the yellow. I can't quite see what's happening at the bottom there. I feel like I probably should know that, but I don't. Right, this has to take the 3 by 3 either there or there, so that's definitely green. And the same is true of these cells. So these all become green. The middle box is becoming constrained. That must be red very clearly. These 2 must be red. This blue is penned in. It's totally penned in. We can just fill it in. That's force. And that's beautiful. So now this purple at the bottom must reach the bottom of the grid. It must take these cells. Ah, lovely. And now if this was purple, this would be a single cell visit, and that's not going to work. So we go in the corner, and this is what we looked at earlier. This is what we looked at earlier. So this can be 15 now, and it must be a 1, 2, 3, 4, 5 quintuple. It's 5 digits, and we know it adds up to 15 with all different digits. So now this must now be, these must all be black, this must be black, because this green can't get in here, which means these 2 must be green, which pens in our yellow, so we get the yellow region all sorted out. And we nearly, oh yes, now my red region is forced as well. It can't go anywhere. It can't get 3 by 3 unless it's those cells. So my red region is sorted out. Let's blacken these cells. And now my green region is, you've guessed it, sorted out. And unbelievably, and this is so extraordinary, isn't it? So we have actually got the locations of all of the regions in the puzzle. And that feels like some sort of miracle, actually, to me at least. Now I'm just going to scan my regions to make sure that I've not got any line segments in them that are too short to be 15 long. It looks like every time they're taking at least 2 cells, which is nice. I think that's right. So presumably that's what we do next, but we must label things like this as 1, 2, 3, 4, and 5. This is a sequence, so that's 6, 7, 8, and 9. These 2 must add up to 15. Those 2 must add up to 15. These 2 must add up to 15. That's a 2-cell sequence. Then they've got a 3 and a 4-cell sequence along with that, which is not very good. Those 2, that's a 2-cell sequence. So that's a 6, 7, 8, 9. That is a 2-cell sequence. 1, 2, 3, 4, 5. Aha! 2, 3, 4, 5. So that's got to be one of these 5-cell sequences, which means this is a 6, 7, 8, 9. Which is interesting. Maybe we've got a what else have we got here? So this one is a 3, a 3, and a 3. Oh, that's very dull. This is a 2, a 3, and a 4. This is a 3, a 3, and a 3. This is, that's a 2. So that's 6, 7, 8, 9. I rather fear there might be, the alarm man might be about to come in, which is early. So let me just see if we can carry on before we get interrupted for a bit longer. So now what have we done? Have we worked out what we needed to here? So now we've got things I can see here, for example, is yeah, this is interesting. This is interesting. Look, I've got a 6, 7, 8, 9 here, and a 6, 7, 8, 9 here. And this square is a 6, 7. So this is a separate pair. So this 6, 7, 8, 9 is the same as that 6, 7, 8, 9. Which means that, and these cells therefore have to go in those 3 cells by Sudoku, and they couldn't both go there, because if they both go there, we know they add up to 15, because that's what they add up to in this box. And then this would have to be a 0, because that's a 3-cell line segment, not a 2-cell line segment. So I think that has to be a 6, 7, 8, or 9. Oh yeah, this is right. I think actually what we might have to do here is to colour these 6, 7, 8s, and 9s, because now I'm sort of trying to work out how this one relates to these two. This is the same as this, and I'm struggling here. Or we might have to get rid of some colours here. I don't know that we need colours anymore, do we? In the sense that do we need to know that this is purple? Now I've delineated the regions. Maybe I don't need colours. Let's risk deleting the colouring of the regions. I'm going to leave the black cells in because we don't need to know. Well, it's quite helpful, to be honest, to see that these black cells are totally irrelevant now, and the lines that are on those black cells are also irrelevant. But what I wanted to do was to look at this, for example. So if you make these blue, you can see that this 15 here is now not the same as this blue, because obviously this digit sees this. There's only 2 ways of making 15 in 2 cells. I probably should state that. Obviously this is either 7, 8 or 6, 9, and whatever it is, this is not that. So that's the other version of 15. That must therefore be blue. This is definitely blue. The other one of these is in one of those 2 cells. And this one therefore is looking at blue, so that must be orange. Which means this one up here can't be orange, and that one is blue, which means this must be orange. Yeah, okay, this is interesting. So we're actually able to potentially highlight some of these 6, 7, 8s and 9s. Now, can we keep that going? What I'm interested in is, can I do these? I don't know that I can. Botheration. Oh, it was going quite well. It was going quite well. And now it's gone wrong again, hasn't it? So now I've got to somehow spot something that's going to be helpful here. What is that thing? You see, one thing I'm seeing, which is a bit strange, is in this box here. I've got one line there and I've got a second line. Now, I've got to put 2 blue digits in this 3x3 box, and I can't put them on the same line, because if I put them on the same line, they add up to 15, and the other digit on that line would be 0, digit or digits. So there must be one of these digits on one line and one on the other. And that logic extends, look. All right, let's flip that logic round and do it with orange in this box. Because I can't put 2 oranges on the same line for exactly the same reasons I couldn't put 2 blues on the same line in this box. So these one of these lines has an orange on it. Well, and the other line has 1 orange on it. So that means that given these 2 can't be orange, and I've got to put an orange on this line, that is an orange digit, which is quite interesting. And now there's another orange on one of those 4 cells, but I don't know what this is. But I also now know, look, that there's an orange on one of those 2 cells. So there's no... Oh, this is getting... I'm almost wondering whether we have to do more colouring here. Okay, so what should we do with our newfound knowledge about oranginess? We shall argue that... Do I need... Oh, I know what's going to happen here. I know what's going to happen. The idea will be, if you can get an orange and a blue onto a line in a box, look at this box, for example. These are not orange. Well, they're not that orange. Now imagine this orange went on this line. Then that would be really constraining, because if you have a 6 and at least a 7, this line would have 13 in 2 of its digits, and the other digit would have to be very low, and it would put pressure on the digits that are available. So I think what we've got to do is to try and get 2 of one colour on a line somewhere. How do we do that? How do we do that? I don't know. I know that... Oh, bobbins. I don't actually know how we're going to do that. I'm sure there is a simple way of doing it, but I'm not seeing what it is. Yeah, so the other thing is that because this is a pair of blues and a pair of blues, one of these is blue. So if I can get an orange on this line, it works just as well. Oh, I can hear the ADT situation. Right, I might have to pause here, I'm afraid. Yes, sorry about this. I will be back momentarily. Right, sorry about that. I'm back, and hopefully there will be no more interruptions. So, what I was doing was I was trying to work out how to do these 6, 7s, 8s, and 9s. Oh yes, and I had the idea that I wanted to get two different colours on the same line. Now, the other thing I think I've been remiss about is it would be very nice to be able to colour these in somehow. So how do I do that? I know one of these is blue. So, sorry, no, that doesn't look very profitable, does it? Blue in this box. Ah, okay, well that's blue. Because remember what we said, there are 2 lines left in this box, and we've got to put a blue onto both of them, because if there's a blue, I've got to put one blue on each line, because if we put 2 blues on one line, those will add up to 15 automatically, and we'll have a broken puzzle. So where do we put the blue on this line? Well, you don't put it here by Sudoku. There are 2 blues in this column, and we know that there are 2 blues here because of these 2 blues, so we can't put it here, so that must be a blue, and that's therefore 6, 7, 8 or 9. So now I feel like I want to know what these blues, or how these blues relate to each other. So I'm just going to, so if I make that blue purple flash, you can see that's the same as that, that's the same as that, that's now not the same as this. So those 3 can all have a green tinge. And now I know that there is a purple in one of these. I know there's a oh no, that's not quite good enough. I thought I was going to get green. I know there's a green on this line. It's not there. Oh no, actually that's no, well, it's not here. So there's a green in one of these 2. I don't really, that's a real nasty pencil mark to do actually. I don't particularly feel comfortable with that. I think we'll resist going absolutely ham on the colouring until I get completely stuck, which will probably be very shortly. So how do we do this? Are we missing some sort of geometry ideas? The problem with these deconstruction puzzles is the geometry doesn't work very easily, because in a regular Sudoku you can sort of do tricks and well, actually I'm going to slightly disagree with myself. So for example, if we look at these 3 leftmost 3x3s, we can say that these 3 digits are the complement of those 6 digits, in the sense that that must be a set of the digits 1 to 9. And that's because we know that these boxes altogether represent 3 sets of the digits 1 to 9. But I know that this column is 1 set of the digits 1 to 9. They're all in the same column of the Sudoku. That's a second set of the digits 1 to 9. So what's left must be a third set. So those 9 digits are a set of the digits 1 to 9. So this digit cannot appear in those 3 cells. No, that's nonsense, isn't it? Can we use that somewhere else? The top of the grid also looks a little, so those are the same digits. I know nothing about those digits, so well, the only thing I can see from that is that at least one of these is orange, because I can't put 2 oranges here because they would be on the same line. Okay, and at the bottom of the grid I know that these 3 cells are and these 3 and these 3 are in the same they form a set of the digits 1 to 9 as well. So can we do anything with that? Yes, we can actually. Yeah, this one works. Right, let me just highlight all of those cells in red for just a moment. these red digits are a set of the digits 1 to 9, and it's just exactly the same logic we just did on the left hand side. Boom, 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 boom. That's clearly 3 sets of the digits 1 to 9. Well, if I deduct that row and that row out, that's 2 sets of the digits 1 to 9 being deducted out of those 3 things. So this is a set of the digits 1 to 9. Now the question I'm wondering about is, where does blue go in this set of the digits 1 to 9? Because we know that there's a blue pair in this triple here. So blue, which can't be in this string of digits, well, could both blues be in those 3 sets? Those 3 cells? Clearly not, because they would add up to 15 and the other digit would be a 0. So I need to put a blue somewhere else in this row. So that is blue, which is, I think, a breakthrough, because now this is blue, which means these two are orange. Okay, well that was nearly a breakthrough. Oh, for goodness. Yeah, no, it is a breakthrough. It is a breakthrough, because now if I know those are blue, this is not blue. So that must be the blue-purple digit. That's the same as that. So that's quite interesting. So there's a blue-purple in one of those. Okay, no, this is not going very well, is it? I still can't quite. Oh no, I suddenly thought maybe I could put this digit here, but I can't, because I don't know whether these two are the same. So maybe I'm meant to colour my oranges as well. Let's just try that. So I will use, shall I use the same colours or shall I use different colours? I think I'll use the same colours. Oh God, goodness me. Okay, that's not a good sign when the alarm starts to go off. That's got to be purple, that's got to be green. So if this is green, that's purple, that's green. And this one, do we know what that one is? Oh. I feel like that would be useful to know what that one is. But I don't think I do. Might be wrong, but I don't think I do. Or these two? Is there some way to know what these are doing? The answer to that is... Well, the answer to that is probably there is a way to know, but I don't think I know what that way is. Oh, there's a purple restriction in this box. These two purples look like horns like this, so one of those is purple. Oh, no, this is useful. Right, that gets me that one. Right, so what we've got to do is look at where purple goes in this box. And because it's in one of those two cells, which I don't really want to pencil mark, it's not here, so that must be green. That is an orange-green cell. So where... Okay, so where does orange-green go in this box now? I think I might have to get really horrendous pencil marking, because I'm losing track of where all these little dominoes are that have got things like one of those is orange-green. Didn't I get something else up here? Or am I imagining that? If this is orange-green... So orange green in this box is massive. Orange green. Okay, right. Here's a point. Where does orange green go in box 4? I've got orange green here locking itself out of there. Orange green here locking itself out of here. Orange green here locking itself out of there. And one of those is orange green locking it out of there. That is orange green. So that is a 6, 7, 8, or 9. So now I want to say there's an orange green up here, but I'm sure. Ah, yeah. Right. This is interesting. So now there is an, I think I am going to have to pencil mark this. There is an orange green up here, which is a 6, 7, 8, 9 digit. Now there's also a blue purple digit up here. I mean, this is completely absurd pencil marking, but because there is a blue purple and an orange green up here, that means that this line contains at least the digits 6 and 7 as a minimum. So this is either 6, 7, 2 or 6, 1, 8. So that's telling us that it has a 6 on it. It has a 6 on it. And it's telling us that, okay, so it's, so it's telling us that the purple blue is not 9 then. Because, in fact, and also, orange green is not 9. So orange green is not 9. We've just learnt that for free. Orange green is not 9. Now we've also learnt that, oh, hang on, I've got, oh, there's all sorts going on here. Right, purple is not a 9, because that would break this as well. So purple is not 9. But also, this one is on a line with this one. This is the blue-green digit. So if this was 9, these two digits would add up to 15, and that would have to be a 0. So that is not 9, and I've got a 6, 7, 8 triple, which means I should now know that the other colour, the one I've not meddled with, which is an orange digit, so it's that orange-purple is a 9. Orange-purple is a 9, which is that digit. That is a 9, because the others can't be 9. So orange-purple. Orange-purple is 9. Oh, so that means, oh, we've done it. We've broken into this, because now orange-green is 6, because that's a do-cell string. So that's 6. Orange-green is 6. Good grief. So orange-green is the 6 up here. Right, these are now a 7, 8 pair. Okay, well that makes sense, doesn't it? So the blue digits have been reduced into being a 7, 8 pair now. So that's going to be nice. We can do some tidying up about those digits. That's a 7, 8 pair. This is a 6, 9 pair now. This is not a 7 or an 8 as a result of a pencil mark. This 7, 8 pencil mark. There's a 6 up here by Sudoku because of these 6s. There is a 1 or a 2 here because we must be adding 9 to 7 or 9 to 8, and this string is adding up to 15. We can, what else can we do? We can argue about the nature of other things too. Okay, there is now apparently a 6 in one of 2 cells in this box. And that's a little bit interesting. For 9, surely, because 9 in this box now cannot go on the line with the 6, because there would have to be a 0 with it. So 9 is in one of 2 places. It's either here or here. Now, can we detect which of those is correct? The answer is probably not, but I'm still going to try. It would be very useful if it was here, because that would give me a 9 up there as well. I don't see how to do that. Apologies if anyone else does. Right, okay, don't see how to do that. Right, those 2 squares are the 7-8 pair. So 7-8 in this box is a little bit restricted. Seven, 8 in this box, is that restricted? How many lines have we got going into box 3? We've got this one we've done, we've got another line there, and another line there. So we've got to keep the 7s and 8s apart on the 2 lines in this box. So that digit has to be in one of those 3 cells. I don't think that's helpful. He says somewhat dismissively, probably with no good reason for being as dismissive as that. Okay, so I've got to do more. Oh, here's a small point. Where does 9 go in this box now? It can't go on a line with a 7 or an 8. So it's got to go in one of 2 positions, one of those 2 positions. Oh, that's a bit disappointing. I thought that was going to be huge, but it's not. So now, these 3 digits add up to 15. So this has got to be 9 and then either 1, 5 or 2, 4. So 9 in the middle box now, is that somehow restricted? Yeah, actually it is a little bit restricted. Where does 9 go in this box? It's got to go on this line in one of those 2 positions. So that means... Oh, that's huge. That's huge. Because that means this line, this is a 4-cell sequence. So this must be 1, 2, 3, 9. Whoa! Adding up to 15, which means that's a 4, 5 pair. Good grief. So now I've got 1s, 2s and 3s into this column to finish off this column. I've got a 6, 4, 5. Oh, I see. The corollary of that was if I'd looked at this, this is a 6 and it's got 2 digits here that don't include 9. So the only way, and don't include 7, 8. So the only way of getting to the number we need is going to be to use a 4, 5 pair. Right, so what's that doing? I wish I knew. What was the... Oh, this isn't 9. And this isn't 9. So these are 1, 2, 3s. Oh, because this is a 9 in one of those cells, and we know that... So imagine this was the 9. These 2 digits would be adding up to 6. So they're either 1, 5 or 2, 4. So there is a virtual 4, 5 pair in this string of digits, which means that cell's not a 4 or a 5. Probably the most useless deduction in Christendom. Oh, I suddenly thought I might be able to put 3 in this row, but I suddenly realised there are 2 places for 3, because I can't put 3 with a 9. Because if I do, I have to put another 3 as well to make the 15. So, okay, so 3 in this box is in one of 2 places. It's in one of those 2 cells. Yeah, okay, so 3 in this box, look, is in one of those 6 cells. So again, we can't have 3s down here, therefore, because we've already got our 2 3s used up in column 2 and column 3. So this is probably not very useful. So this is 3 with either 7 or 8. So these digits are either, so this is a 3, 4, 5, with one of them being a 3. Oh, bother. Okay, I don't know if I can do that. That almost felt important, but I don't think it's actually that useful. Right, okay, so what else is it that I'm meant to be appreciating about this? It's going to be that this digit is a 7 or an 8, so these two cells have to add up to 7 or 8. Is that helpful? Not really. This can't be a 7 or an 8. Oh, maybe it's the green digit. Oh no, I've already looked at this before. There's a green digit, I think, in one of those two. The blue-green digit. But I think that's all I can say about that. So this cell here is at least, if that's 8, that's 3. That's got to be a 4. So it's 4, 5, it can't be 6, and it can't be a 7, 8. So that's 4 or 5. 3, 4, 5. 4, 5. Okay, okay, that's quite interesting. So whatever this digit is, it finds a friend here and ends up there. So those squares are only 4, 5s and 6s now, which is marginally interesting perhaps. But this is where we get the problem with deconstruction puzzles, because column 4 is totally useless. You can't argue anything Sudoku wise about column 4 because there are not 9 white cells in it. Oh, hang on. Hang on, where does 9 go in this box now? That's a good question. I don't think 9 can go on this sequence, because if 9's on this sequence, the minimum I'm adding it to 9 is 9 plus 4 plus... This is at least a 4, and a 1-2 pair would get 7, and that's 16. So 9 is not on this line, so 9 goes here. Wow. Wow. Which means this isn't 6 anymore, so that's the 6. So this digit is now not 3, because we know we need these two to add up to 6. Does that mean this is 3? Oh, perhaps it doesn't. No, these 3 digits are adding up to 9, aren't they? Oh, but this is 6, so that means that's 6, which means that's 9. Ah, okay, so that's good. That's good. That's still progress. Any sort of progress, I think we have to take with gratitude. So that becomes orange and purple. So now 9, 9 is not there anymore. And, oh, botheration. I don't think I can get the 6, but I can get the 9. And I will take that with gratitude, as I just explained. Now these squares have got to be 1, 2, 4, and 5, because they must add up to 6, which means, oh no, I thought that was a quadruple, but that can be a 3. Oh, botheration. I don't believe it. Okay. Oh dear. Oh dear. Oh dear, oh dear. Okay, so now... I don't know what to do. Can we argue about... Oh, we can probably get 9 restricted in this box now, I'm seeing, because 9 and 9 go together, locking a 9 onto this one. So now... Now what do we do? We can use that to argue about Well, actually, no, that is good. I'm just spotted I've got a pencil mark 9 there. So this is not 9, that is 9. Epic. So that is a 9. I shouldn't be surprised. This is relatively tricky. It is a Sudoku made of a line, after all. So 1, 2, 3, 4, 5. So how many 9s have I got in the puzzle? I have got lots of them. I've got 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. I've got 2. No, I must have 8. 1, 2, 3, 4. Oh no, I've got. Oh yeah, look, I can get this one. Good. Let's award this the mantle of orange purpleness. And I've got. Oh, this is silly deconstruction rule again. So I've got 9 in one of these, but literally no way of getting it. Because there don't have to be 9s looking at all the other 9s. Ordinarily, if you've got 8 9s in a Sudoku, you could happily fill in the 9th. In this puzzle, not so much. Oh, hang on though. Where is this height? Right, there's a 7, 8, 7, 8 here. Now I know one of those digits is in this column, but the other one isn't. So where does it go? It can't go on a line with a 9, because it will add up to more than 15. So this digit goes... Yeah, oh actually, hang on, we know it's the purple digit as well that's here. So the green, it's the green digit. Whoa, that's some sort of emergency vehicle going on outside. So the green digit goes here. This is blue-green, therefore it's a 7 or an 8, which means that its home in this box is now unknown. Unknown! Ah, you rotten thing. So this is 7 or 8. So these two add up to 7 or 8. They don't use 6. But they do use 3, don't they? Because 9, yeah, this is nice. There's a 9 on this line, so the other 2 digits on this line add up to 6, so they can't be 3, although they would have to be double 3. So where does the 3 go in this box? It goes on that string of digits, which means that's not a 3, which means this is a 3 by pencil marking, which means that this is not a 3, or these are not 3s. I've now got a 1, 2 pair here. Good grief. So I've got a 4, 5 pair over here. I've now got a 1, 2, 3 triple in box 6. And I've got my 3 here, which is on a line with a 7 or an... Oh, goodness, that doesn't do anything. No. Oh, for goodness sake, you naughty puzzle. You rotten thing. You rotten thing. Okay. So, still, we resist. Right, so these squares are from 1, 2, 4, or 5. I think we already knew that. There's a 3 in one of these. I feel like 3s might be more useful than I've made them so far. Because we've got to remember that on a 3-cell string, you can't have a 9 with a 3. I was thinking I could get rid of the 3 from there, but I can't, because that is a 2-cell string. That can't be a 1, because this can't be a 6. That's fairly obvious. So this is 2 or 3, which means the 1 in this column is going up there. One of 2 places in the column. So there's no 1 on this string of digits. Oh, so one in this column now is either here or here. Oh, but it probably can't. Right. Oh, in fact, it is going to be. Oh yeah, sorry. This is not helpful. Right. Where's green 7 and 8? This is tricky. It's really difficult. We shall now argue about the nature of... Does that 3 have to go with a 4 or 5 on this line? So we've either got 7 plus 3, so we need a 5, or we've got 8 plus 3 and we need a 4. So this is a 3. so there's now there's a 3, 4, 5 triple in this row. So this becomes a 1 or a 2. That becomes a 4 or a 5. And this digit is a 1 or a 2. And that is very beautiful for no reason I can think of. Okay, yeah, so this is 9, 4, 5 now to make this line work. So there's a virtual triple. Okay, yes. So there's a virtual 4, 5 pair between these 3 cells, which means that these 2 cells at the bottom are a 1, 2 pair, which means these are a 3, 4, 5 pair, which does nothing because this column has not got all its digits in it. No! Oh, for goodness sake, this is very, 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 very difficult. But how long have I had? Oh, it's hard to tell because I had to restart the video. I had a long time. But I hope you'll forgive me. This is not perhaps the easiest puzzle that we've ever seen. Right, where? Oh, look, one of those is a 6, apparently. And I've got 2 6s looking at it, so that's a 6. Isn't it funny how I sort of just looked away for like a second and suddenly you can see things you missed. Right, so now, so now I need my... this digit has now got to go there. That's gorgeous. So I've got another digit. That is a blue. That's this digit. So now this digit is a 1 or a 2, which gets a pair there. It doesn't do anything again. So now the purple blue digit is in one of these cells. And literally, I don't know which one. Oh, hang on. Here is a small point, though, because look, there's a pair now of 7 8s. So, and what we can't do here is put the 7 8 there, because that would have to be a 0. So that is a 7 or an 8, and that gives us a pair in this column on 7 and 8. And that, of course, I can hear you saying it cacophonously, does nothing. There's a 7 or an 8 in here. This is so difficult. It is so difficult. It is definitely difficult, but all is forgiven, frankly, because the fact this exists is so mad. Okay. For goodness sake. Right. Okay, here is something rather cool. That cell is not a 3. That cell is not a 3. And the reason it's not a 3 is because of the nature of 4 and 5 that would have to accompany this. So look, these digits are the same. I don't know what they are, but they're the same. Now, if this was a 3, then these 2 digits would also be the same. And the implication of this line and this line would be that these 2 digits would be the same, because to get to 15 we would be adding the same numbers up. So those 2 would be the same and they'd repeat in the row. So that must be a 2. Which gives me a 1 here and a 5 here. And therefore this square is a 3. Aha! So now are we away? The answer is maybe not. Although that means these squares have to be a 2, 4 pair by Sudoku, which means that is not a 2. It means this is a 5, and therefore this is an 8. So that means that's an 8, that's an 8. Oh, come on, that could be huge. Oh, this is huge. So blue-green is now 7. Blue-green is 7. And look, this line now needs a 1 on it, which means that's a 2. So that must accompany... Oh yeah, okay, so this is getting done. This is getting done. This has got to have 3, 5 on it, which means this has got to have 4, 9 on it, which means that becomes a 5. That becomes a 1. That becomes a 2. This line now does add up to 15, so it works. Now this square will be a 4, and hopefully that adds up to 15, and this adds up to 15 in a different way. So we've got the 3-4 pair here and the 5-2 pair here. So now, has this done it? This 2 means that's a 2 and that's a 4. So those two squares there have got to be a 1-5 pair. And that might be mattering somehow. Don't know how. That square is now obviously orange-green. Oh, that was so exciting, and it's stopped again, I think. Okay, so that's a 1 or a 3. Oh, come on. Come on, you silly man. Actually, there's got to be a 7 or 8 on this. Is a 4-cell sequence. So how could this be a 5? That surely won't work, because we know one of these is a 7 or an 8. If we add 7 to 5, oh no, we could do it with 1 and 2. Although the 1 would go here, so no, we couldn't. So this can't be 5, because the 1 would not be available. So the minimum this would be 2 plus 3 plus 5 plus 7 or 8, which is more than 15. So that's 1, that's 5. Now how does this work then? These two have to add up to 10, which means that's got to be a 2 or a 3, and it can't be a 2, so that's a 3, that's a 7. Which means it is the blue-green digit, and that means that one of these two is the purple digit, and is the 8. Don't know which one. But the 8 is going to need 1, 2 and 4 to help it finish. So this has to be a 4. And that 4 fixes the 4 and the 9. So these are a 2-8 pair. This is so... Oh, the 2-8 pair and the 3 here, that's the 3 and the 5. That's great. Okay, that feels like progress again. This 7 is fixing the 7 and the 8 here. So now I can purplify one of those and I can greenify this one. This is not a 4 anymore by Sudoku, or a 1. So this is 2 or 5. So this needs to be a 1 or a 4 to make this 2 add up to 6. Keep going, come on. I think this is nearly cracking. Right, look at this row. We must have a 1, 2 or a 3 into that cell by Sudoku, and that gives me a 1, 2, 3 triple here, which makes this an 8 and this a 2. And now these squares at the bottom of the column must be a 4, 7 pair, and somehow that's not resolved. I don't believe it. So now I've got 11 here, which means these two squares add up to 4. So they are a 1, 3 pair, which means that's not a 2. And I've got a 1 here that I hadn't noticed. So that becomes a 3, that becomes a 2, that becomes a 1, that becomes a 3, that becomes a 1. We get a 1, 2 pair, which is resolved over here. This is now a 5, so that means this is a 1. 2, 1 go into the grid. Good grief. That's a 3 by Sudoku. That's a 4. That's a 5. This is not 5. Now, what do we need along this row? 3, 4 and 7, I think. So that square is 3 or 4 only, which means that this square is the 7. This is the 4. That's not 4. And so probably it's just these lines at the bottom that will figure everything out, which is very exciting. So this column needs 3 and 6. So the 6 goes here. The 3 goes above it, which gives us the 4, which gives us the 5 and the 4 in that column. That's now a 3, that's a 5, that's a 4 by Sudoku. This is 7 or 8, but I'm not going to claim I know which, except I do, of course. I've got 7 there, so that's got to be 8. So that's 8, that's 7. And now I need 7 in one of these, and Sudoku tells me it's this one, and that's a 2. And that is the puzzle, I think. I've just got to colour it in properly. So every 8 gets purplified. Every 7 only. I only want 7s. Find 7s. 7s become blue and green. Every 6 needs to become green and orange. and every 9, did I colour the 9s? I did. They become orange and purple. Did I colour anything else, or was it just 4 colours and the 1s, 2s, 3s, and 4s and 5s were left out? Well, what's not going to work is the tick button, I'm afraid, today, because the tick button will just do this. What? Okay. I don't know how the tick button worked there. That's very, very weird. That must be... I don't know whether the software has checked... I don't actually know how the tick buttons worked at all. I don't know how it did that. I suppose I'm just looking at the URL that Mark sent me, and it's enormously long. So perhaps it's possible Jay Dyer has put the solution into the. Well, if that's correct, and this has really checked that I've got it right, that's absolutely amazing. I'm just blown away by this. Can we just take a moment and think about what we have just witnessed, which is a puzzle, a Sudoku puzzle, constructed out of a line. I mean, I'm going to call this video a Sudoku with no given digits and a line, and just one line. And people won't believe it. They won't click on it because they'll think, well, that's so stupid. Don't be so stupid. How could that possibly be a thing? And yet, Jay has created a puzzle which is just made up of a single line. It is a startlingly original and brilliant puzzle. It's not easy. I'm not going to... Well, no, it's not easy. It's just not easy. The beginning is fascinating. The fact that you can even plot the regions is fascinating. And then it disambiguates, basically, because you can do so much work with 6s, 7s, 8s and 9s. It's extraordinary. What a puzzle. That is one of the greatest Sudokus that has ever been made. Full stop. Hats off to Jay Dyer. You have made one of the greatest Sudokus of all time. Extraordinary. Thank you for watching. It's a long video. I hope you understand why. I hope that you'll forgive me. Let me know in the comments how you got on. I'll be fascinated to know how many of you have solved this one. Yeah, that will live long, long in the memory. And we'll be back later with another edition of Cracking the Cryptic.